Hello, my name is Hank Ashbaugh. I'm from Tulane University, and it's a real honor to be here in virtual San Francisco at the 2020 AICHE National Meeting. I'm going to talk today about some work I've been doing with collaborators of mine, experimental collaborators of mine for the past several years, looking at deep cavity cavitands. In particular today, I'm going to talk about the spontaneous drying of nonpolar deep cavity cavitan pockets in aqueous solution. Now, typically when people think about looking at nonpolar solutes in water, you typically think of small spherical things, maybe larger things like a micelle or a protein, but typically they have a positive curvature. But there's also a lot of interest in trying to understand what happens as the size gets bigger. And if I'm considering a hard repulsive solute surface, as this solute gets bigger and bigger such that it approaches a flat, hard wall, there are distinct statistical mechanical predictions about what water will do at that wall. In particular, from the wall theorem, the density of water in contact with that wall, the ratio of that contact density divided by the bulk density is given by the bulk pressure divided by the ideal gas pressure applied to the bulk water density. And if you put in the saturation pressure of water, what you'd find is that that density of water in contact is about 1/100,000th the density of water. So much so that the expectation is that water will actually form a thin vapor film in contact with that wall, where as you move away, you will actually transition from the vapor to the liquid phase through a liquid vapor phase transition, and that water is basically going to try to pull away from and de-wet that wall. Now, ubiquitous van der Waals forces will frequently pull that in, but there is still a tendency to want to try to de-wet that wall. And so we can actually observe this from molecular simulations in which you look at plates where you have plates in water, and if you bring two plates in water that want to de-wet, when they hit a critical distance such that you're at this critical separation, that vapor film actually grows and you can actually stabilize a vapor bubble between the two plates, in this case in water, or between in a Leonard-Jones, two-dimensional Leonard-Jones fluid, where you can actually nucleate this vapor phase. And so you get spontaneous drying in the case of non-wetting walls. Now, these are for actually two walls coming together. And a question that we might have is, could we actually induce this in a single surface? And one way that you might hypothesize that you could actually do this is to keep growing this solute surface such that you pass from positive curvature to negative curvature. And you may hypothesize that if you get a tiny negatively curved pocket, that you could, in fact, get water to retreat from that pocket and de-wet the pocket. And so based on these phenomenological predictions, we decided that we wanted to look at a class of molecules called cavitands, or so-called deep cavity cavitands, or in this case, deep cavity cavitan octaacid. This is a host molecule that is built on a resorcerine base, has 3 layers of aromatic rings around it to build an 8 nanometer in diameter hydrophobic pocket that's about 8 nanometers deep. And these are made water soluble by having 8 charged carboxylic acid groups attached to it. And these have been synthesized experimentally by my collaborator, Bruce Gibb, in the chemistry department at Tulane University. And so we start with this octaacid case, and we just ask the question, what does water think about going inside this pocket? And so we see here the octaacid with its pocket, and we just do the simple thing of just simulating this with a GROMACS and looking at the probability of N waters residing within this pocket. And over the course of our simulations, we will actually see the occupation number fluctuate over time, centered around an average occupation number of 1. And so about 4 waters on average will want to reside inside this pocket, and it is wet. And so you actually get this distribution, and it fluctuates on the order of about a picosecond to 2 picoseconds per time scale. But if you look down here at the low occupation probability, what you actually see is there's actually a lower probability of having 1 water molecule in than having 0 water molecules in. It's slightly less, and we refer to this as a fat tail. So you might say, is there any way that I might be able to modify this molecule to then change the wetting properties? And so we've looked at, perhaps we can replace these hydrogens here with a methyl unit to kind of grow the pocket up. And when this can be synthesized, this is so-called tetraexomethyl octaacid. And when we look at this, what we see is that the occupation probability for TexMOA is about the same as for octaacid. But if we move these methyls from these upward pointing positions to an inward pointing position in a so-called endo position to make tetraendomethyl octaacid, what we see is that the probability distribution of water dramatically changes, where we still have a minimum here at probability of 1 and a maximum somewhere now at 4, but now we see that over 70% of the time, the molecular simulations predict that this pocket should be completely empty. Now, you may ask, and so we get what looks to be apparently an equilibrium between a low density or a de-wetted, quote, vapor phase and a higher density, quote, liquid phase. Not really a liquid and a vapor, but still analogous to it in some ways. And so you might ask, could we actually verify this experimentally? Now, as we saw before, TexMOA and octaacid are wetted. Water likes to go into it. But if you imagine that you could pump the water out of there to create a void, what you would expect is that the partial molar volume of the dry species would be considerably greater than the wetted species. And so we have actually synthesized each 3 of these host molecules and performed densimetry experiments as a function of weight fraction of the added host. And if you do that and you use this formula, get the slope of this line, you can actually calculate the partial molar volume at infinite dilution for each of these host molecules. We can also gather this from our simulations. And when we look at the experimental and simulation data, what we find is that experimentally and simulation-wise for octaacid, the base case, we get basically the same volume. If we look at TexMOA, we get a slightly greater volume, which is about 73 to 80 centimeters cubed per mole greater. And if we ask what that comes from, it actually just comes from the methyl groups, because if we look at the difference in the molar volume of alanine versus glycine, the amino acid, that is the partial molar volume of a single methyl group. Multiply that by 4. What we see is that this partial molar volume is basically that associated with the methyl groups. But when we go to tetraendomethyl octaacid, what we find is that these volumes are considerably greater and so much more than the 73 that we get an anomalously large volume that we could attribute to drying of that hydrophobic pocket. And you may ask, well, is that really drying? And so from our molecular simulations, we can actually look at the partial molar volume of each 3 of these species as a function of the number of molecules inside the pocket. And what we find is that while we have differences in the partial molar volumes of TexMOA and TMOA, experimentally and simulation-wise on average, what we see is that as a function of the number of waters inside that pocket, it's a decreasing function of the number of waters inside that pocket, but basically TexMOA and TMOA have the exact same partial molar volume. The partial molar volume of OA is significantly different or lower, but it has about the same functional difference. And in fact, if we add the partial molar volume of the 4 methyl units from simulation, which is 81 centimeters cubed per mole, we get agreement between the 2, such that the Cavitan volumes really are indistinguishable when we compare them on a hydration basis, and that the volume anomaly comes from the reweighting of these different volume states when we consider the probabilities of observing distinct volumes. And so this is really a manifestation of the drying phenomena. Now, what might this drying phenomena actually do to change the properties of this solute? And if you can think of this cavitand, it actually is a host pocket. It can bind guests much in the way that a cleft in a protein can actually bind guests. And it has been proposed that the wetting behavior in protein clefts can really change the thermodynamics of binding, such that if you're looking at a nonpolar cleft in a protein, it's been proposed over the past 10 years that the driving force for hydrophobic species to bind to that cleft is actually enthalpically driven and entropically opposed, which stands in distinct difference from typical interpretations of hydrophobic interactions and forms what we call the non-classical hydrophobic effect. And so we ask, does our solute, or our wetting, de-wetting states give any insights into this? And so experimentally, we've performed ITC experiments, isothermal calorimetry experiments, to look at binding of sodium alkylates to both octaacid and tetraendomethyl octaacid for hexyl through decyl sodium alkylates. And we, from these ITC experiments, can get the thermodynamics, the free energy, enthalpy, and entropy of binding. And when we look at them, and then take the difference between guest binding to TOMOA versus OA, what we find is, number one, that binding to TOMOA is more favorable in terms of the free energy. It's enthalpically more favorable and entropically unfavorable, keeping with the idea that this is a non-classical hydrophobic interaction. And so we asked, can this be moderated by the drying phenomena? And so if we're actually going to get guest binding to a pocket, we are ultimately going to first have to empty the waters from that pocket to be able to get the guest in. And so drying could play a significant role. And so we've looked at the drying distributions, or the occupation distributions of water in octaacid as a function of temperature. Here are these probabilities, and we can see that the probability, or the free energy for drying this guest is proportional, or host is proportional to the probability of observing a dry state or empty state. When we do it for TOMOA, we get these distributions here as a function of temperature. And we can then look at the thermodynamic differences. And number one, what we find is that, non-surprisingly, drying for TOMOA is more favorable. It is enthalpically more favorable and entropically unfavorable. And the magnitudes of these free energies and the thermodynamic constituent properties that we find compare quite favorably with those what we got from looking at binding experiments of guests to hosts. And so we conclude that the drying thermodynamics mirror the experimental binding thermodynamics. And so, in fact, we believe that this drying can actually manifest itself in the guest binding properties of hosts, and tells us that perhaps we can actually design hosts to bind guests with specific thermodynamic properties. And so, in conclusion, what I hope I've been able to convince you is that we can look at the wetting of synthetic supramolecular hydrophobic pockets, or host pockets, that can be tailored by functionalization of the portal to the pocket, the entrance to the pocket. And that the drying of the hydrophobic pocket impacts the volumetric and host guest binding properties of those cavitands. If you want to get more information on this, this work, please look at our article that just appeared this past summer in Nature Chemistry. I would also like to thank the other people who did this work, including my graduate students, Wes Barnett and Du Tang, our synthetic collaborator, Bruce Gibb at Tulane University, and our experimental collaborator, Dor Benamatz at Purdue University, who did the densimetry experiments. I'd also like to thank the National Science Foundation and the Louisiana Optical Network for providing both computational and financial resources for this work. And with that, I would be happy to answer any of your questions.